dishes, put these biofilms on them to see if they killed them, and they did. And so this story from about 2005 until just a couple years ago very rapidly grew that not only were ants harvesting leaves to help farm funguses inside their colonies, which is amazing enough, but that they had these bacteria with antibiotic properties that also helped the funguses from competing fungi. Right? Wow, this is awesome. They're not just growing plants, they're medicating plants. Well, recently that's turned out not necessarily to be true. So I added a couple question marks because people are less sure of this story. It turns out when you use these bacteria against the funguses that compete with the funguses they're farming, they don't have much of an effect. It's more likely that the biofilms have some protection to the ants in terms of ant disease. Right? So it's not that the ants are helping the funguses here, it's that the ants have certain bacteria that grow on them that help protect them from whatever diseases ants succumb to. I don't know that story very well, but I know just enough about it to know that there are question marks in this kind of simple explanation. So when I told this over the course of about 10 seconds, 6 weeks ago or something, I just wanted people to know, we're not super sure of these connections. Right? And that's why I put the question marks on. That's evidently before I was putting links to reviews. There's a review by Ulrich Mueller about this, and he's a really good writer. I happen to have known him very casually about 20 years ago. I made fun of him in a public place. It was hilarious. He's a really nice guy. He's a great scientist.
Can you go over question 5 on the semicolon?
Maybe. What was it?
It was the operating efficiency and negative density and how you define that on the European graph.
By the way, I'm going to run out of juice pretty soon. I just noticed I only have like 30. My everything about me is getting old.
Just when you're answering it, just.
Can I do this one with a magic marker? Can't use a little more? Alright, so I'm going to run out of juice. This should pop back out in a second. So the question is positive and negative density dependent growth and the Ali effect. So the essence of positive density-dependent growth is as you get bigger, you grow faster. As you get smaller, you shrink faster. So it's positive density-dependent because whatever direction you go, that accelerates the process. I know you can't read that because this is a big room, but that's what it says. So our classic curve that we had in class here had a birth rate in blue and a death rate which was red when we get black here, right? And here's the Ali effect. Notice if you get bigger from the Ali effect, this is the Ali effect in this space, Ali, I am the greatest. If you get bigger here, then birth minus death is greater than 0, right? So the further you go this way, the faster the population grows. This is positive density dependence. And it goes the other way, So if we go less than whatever this cutoff is for the Ali effect, then birth minus death is less than 0. The population is shrinking. So here's where it's weird. We have positive density dependence where the population is small. This is an unstable equilibrium. If we perturb our population from this cutoff, and this cutoff incidentally is some kind of isochron, but from this cutoff, if we perturb it this way, it goes further and further and further away from that equilibrium in a positive direction. If we perturb it this way, it goes further and further and further from this equilibrium in that direction. So this is an equilibrium because births minus deaths is 0, and it's unstable. And it's positive density dependent growth. Okay. Now that's in contrast to this, which is our carrying capacity. Here, as we increase, if we start someplace like this, moving that way, we're still increasing, but we're increasing slower and slower and slower and slower, which means it's negative density dependent growth. As the population gets bigger, its growth slows. Negative density dependence. And likewise, here, the same thing the other way. So negative density dependence, as population increases, growth slows. Does that help? I've already forgotten your name. Victoria. Did I know that? Okay. But I didn't forget your name, I never knew.
That's okay. So for negative density, kind of as the population increases, growth slows. So as the population decreases, with the growth, would it decrease slow?
If you're here and you're decreasing, it's going to slow. Or on the other side. What's important, Victoria, is that this is a stable equilibrium. And this is a stable equilibrium we've talked about a lot. It's the carrying capacity. I'm sorry? This is carrying capacity. We don't have a name for this equilibrium, but it's the cutoff for an Ali effect. Joey.
So that leaves, because there's 4 options, so that leaves density and growth to be on the left-hand side on the death rate.
Oh, those aren't options. You don't have to pick all of those options.
Oh,
And if you notice, there's also none of the above.
Oh, it does, okay.
So there could be multiple arrows with the same letter, or there could be none of those arrows pertaining to the question. I don't like process of elimination, because that's not the way the world always works.
Yeah. So then, is there a slot on this graph that would be density?
Is there a spot on this graph that says density independence? No.
What would that look like?
What would that look like? That's a great question. And I even know the answer, because usually when I say that's a great question, it means I don't know the answer. Remember, the growth rate is the difference between birth and death. If the difference between birth and death is constant as a function of density, then it's density independent. So here, this is constant, and it's births minus death, which is r, little r. So that means there's no change in r as a function of density. It's density independent growth.
Do you only see that in like closed systems?
Closed systems.
Like, would you see constant birth and death rates in like a open natural environment?
Oh, maybe. Maybe. I could imagine situations where you would. Okay, so this is what we think happens that when it leads to exponential growth, right? Because if you've got a constant, and remember this is per capita.
So it's like people.
It could be people. I was thinking mosquitoes, but 6 in one, half a dozen the other, right? Yeah. It's not. You're Victoria. You were. Oh my God. Regina is behind you. She's also. This is gonna kill me. I'm not going with Wilhelmina. Julia. Okay.
It was just like with your graph before. So can you just say that the definition of the unstable equilibrium point is that it's positively density dependent?
Only if the x-axis is density. So there are cases where you've got unstable equilibria that have nothing to do with density. I should know your name because I've seen you like a dozen times.
Nathan,
We'll go with that. I can't even hear it right now.
so do we have positive density dependence from the beginning or last graph? From the beginning?
Loudly, I'm getting some chatter.
For the last graph, do we have positive dependence and density dependence from the beginning to the midway?
I don't know exactly where I'd say that it cuts off. That's my guess, is that as those differences shrink, then you've got negative density dependent growth. The difference, which is the growth rate, gets smaller as you keep going to the right at roughly the middle. So that's an astute observation. You win. Jeff?
Yes,
Okay.
I have another question, but not pertaining to this.
Okay.
Can you go over the type 1, type 2, and type 3 functions?
Do we have more questions on density dependence and birth and death rates before I go on to something else? Yes, there are lots of questions. This is your chance to ask. Okay.
So how did which was the answer number 5?
I don't remember what number 5 is. Let me see if I can pull it up. But I might ask you to ask that question in a slightly different way. All right, so well, I don't give you, I haven't given you things to choose from there.
Right, exactly.
There are 2 number 5s. This is why I taught statistics, because I can't count.
It's to the right of
Let's
the
see it. In the diagram left, several points are labeled. Please put the appropriate spot in the which one. And F is none of the above. Stable equilibrium. I want you to tell me which is the stable equilibrium. No. I'm literally asking you right now, which is the stable equilibrium? Right. Easy. Okay, so let's go to the next one. Positive frequency dependence. I'd say it's A, because B actually points to a single line, which is, actually it could be A or B. That's a good point. There's some ambiguity there. It could be A or B. Negative density dependence. I think C would be negative density dependence. And then density independent growth? None of the above. It doesn't exist on this particular question.
Thank you.
All right. Other questions before we go on to type 1, type 2, type 3? Is this about growth? Okay, what's your question? Loudly, please. I think I'd have to be a little bit careful. So the difference between A and D and the other ones that I intended was that A and D point to equilibria, and B and C point to lines. And so one of the things that's important to recognize is that one of those lines has to do with birth rate, and one of those lines has to do with death rate. Those aren't necessarily growth in and of themselves. The difference between them has to do with growth. So this is a question I came up with as I was kind of running here. I had to make sure it was a little bit better sussed. But this is the kind of question I'd ask with multiple choice. I'd give you some figure and say, here are a bunch of questions about this figure, answer them for me. All right, now before we had a question down here about type 1, type 2, type 3, that I'll remember you, and I'll go back to you in a second. Type 1, type 2, type 3.
Okay, we just go over it.
Can you ask a question that's more...
Type 2. Type 2.
Yeah, you
I
can.
see like a plateau.
All right. So these are called functional responses. Where we have density of prey and the number of prey per predator.